Okay, so moving on from here, I need to go to the computer, and now we're going to move on to the next section where I'm going to talk about another kind of valence bond that you need to know about that is very important. So you might remember that maybe the last presentation I was kind of talking about what a particular kind of valence bond called a sigma bond was. And so let me talk a little bit about that again here. So what is a sigma bond? So sigma bonds occur when you have two orbitals, whether they be atomic orbitals or hybrid orbitals, or maybe a hybrid orbital from one atom and an atomic orbital from another, overlap. And they overlap end to end. And the result of that is that the area of the overlap is going to be between the nuclei of the atoms. So that's one requirement for the sigma bond. So for example, here in the sigma bond for these two s orbitals here, you can see the area of overlap between the nuclei of the atoms. Now another sort of important fact about a sigma bond is just notice how the electron density is symmetrically arranged around that yellow axis between the nuclei. And if you have that situation where the electron density is symmetrically arranged around the axis, it is called a cylindrical symmetry for the electron density. So you can get a sigma bond like this by overlapping two s orbitals, which we see here, but also you can do it with p orbitals. And so if you overlap a p orbital with another p orbital and the lobes are facing each other between the different atoms, so here we're going to overlap this lobe of the p orbital of the left atom with this lobe of the p orbital of the right atom. We're going to push them together, and so what you can see here is that we have now created a sigma bond between two p orbitals. And basically it's a sigma bond because it's the same characteristics seen with the s-s overlap. And so again, what you see is you see electron density in the overlap between the nuclei of the atoms, and you can sort of see that that electron density is symmetrically arranged around an axis that might connect the nuclei of the atoms. But here's the thing, this is one kind of valence bond. You can have other kinds of valence bonds that form where you don't necessarily have the electron density that is exactly between the nuclei. It may be sort of above or below the nuclei. And furthermore, it may not be that the electron density is symmetrically arranged around an axis that connects the nuclei. So let me talk about that example there, which I just described. So this is the case of a pi bond. So pi bonds, for example, are covalent bonds formed by sideways overlapping orbitals where electron density is concentrated above and below the plane of the nuclei of the bonding atoms. So let me give you an example of a valence bond that can form between two orbitals, but it's not a sigma bond. Instead, it's a different kind of bond called a pi bond. So what you are seeing here is we have one p orbital from one atom here, and we're going to press it close together with another p orbital from this other atom here. And so what you can sort of see is that when you bring these p orbitals close together, there is really no overlap of those p orbitals in that area between the nuclei of the atoms. That does not happen. Instead, you can sort of see where the lobes of the p orbitals are. They are either above the nucleus or below the nucleus. And so it's in those locations, either above the nucleus here or below the nucleus here, where those p lobes from the different atoms tend to overlap. And that area of overlap is called a pi bond. You can see in a pi bond, there are really two regions to it. In a single pi bond, you have a region of overlap that is above the nuclei, and then you have a region of overlap that's below the nuclei of the atoms. Okay. What I want to do now is I want to sort of explain to you how can it be that a molecule can have both sigma and pi bonds at the same time. And so the best way for me to describe that is by taking an example molecule. And the molecule we're going to be looking at is the C2H4 molecule, which is called ethylene. Another name for C2H4 is ethene. In fact, fruit release this gas, and this gas tends to ripen the fruit even more. So, and also ethylene is kind of an interesting molecule in that this is one of the most highly produced small molecules in the nation, because it's this molecule, when it's polymerized over and over again, that makes up plastic bags that you get from the grocery store. I want to take a Lewis structure of this molecule, ethylene, and draw a picture of it and show you where the sigma bonds are in the molecule and where the pi bonds are. So I'm going to go back over here to the board, the glass board. And so the first thing I want to do just to get oriented is I'm going to work in the corner here. And what I want to do is first write a correct Lewis structure for ethylene. You sort of see it there, but I actually want to go through the process so you can see how I got the double bond. That's kind of important. So you have C2H4. And so what you have to do is count up valence electrons. And so you have carbon, which has 4 valence electrons, and there are 2 of them. And so you have a total of 8 valence electrons from carbon. So hydrogen has 1 valence electron, and there are 4 of them. And so you have a total of 4 valence electrons from the hydrogen. So we have, it looks like 12 valence electrons we have to mess with. I'm going to kneel here just for a second. And so we have 6 pairs that we have to deal with. Okay. So let's go ahead and figure out this Lewis structure. And so what I'm going to do is I'm going to arrange atoms here. So we have a carbon atom here, we have a carbon atom here. Hydrogens are on the outside because they need to be, because hydrogens are always on the outside of a molecule. So now let's go ahead and put in the 6 pairs of electrons. So we have 1 bonding these carbon atoms, 2, 3, 4, 5, and then it looks like we need to stick a lone pair here on this carbon here like this. And so let's go ahead and count octets. And I think what you can sort of see here is that this right carbon has an octet, but this left carbon does not. And so what we can do to make sure that all carbons have octets is I'm going to remove this lone pair here from this carbon. I'm going to move it into the bond between these 2 carbon atoms. And now you can sort of see is that the carbon atoms have octets and the hydrogens have duets. So this looks like a good structure. And so you can see that carbon has a double bond like this. And then there are hydrogens attached to it like this. And so this is a perfectly good Lewis structure of this molecule, C2H4. Okay? All right. So what I'm going to now do is to give myself an idea of what this molecule looks like in space and where the sigma and pi bonds are. I'm going to write electron configurations for these atoms in this molecule. So here we have carbon. And so one thing I want you to note is we're going to have to figure out what the hybridization of each of these carbons is. So we have to write the electron configurations with hybridized orbitals. So if you look at the carbons here, what you can sort of see is that each carbon has 3 electron groups. And so if it has 3 electron groups, there are going to be 3 hybrid orbitals that carbon has. We create them by grabbing 1s and 2p atomic orbitals. And so they're going to be called sp2 orbitals, and there are going to be 3 of them. So how would I write that out in terms of configuration? So we have 1s electrons, they're always there, and then we have these, now we have 3 sp2 orbitals. So these are sp2 orbitals, and they're in the 2nd energy level. Okay, now you will note that when I created these 3 sp2 orbitals, I grabbed 2 of the 3 possible p orbitals. So importantly, there was a p orbital that was left that I did not grab, and it's still there. Now, let's go ahead and put electrons into this. There are 6 electrons, so there's a pair here with this carbon, and then there are 4 electrons. 3 of them go into the sp2 orbitals, 1 goes into the p orbital. Now, there's a second carbon that is bound to this one here, So I'm going to write out the configuration for carbon here. Let me get a more live pen. So we have carbon here, and so we have 1s, and then we have 3 sp2 orbitals, which are in the second energy level, and then we have a p orbital that was not hybridized. And so here are the six total electrons here for this carbon atom. Okay, now let's go ahead and start thinking about where we can put hydrogens in this molecule and what particular bonds they can form into what particular orbitals in carbon that they can bond to. So there's one obvious thing that I see. So one is that each carbon will bond to hydrogens. So let's just take this top carbon and stick on hydrogens. And so we're going to put one hydrogen here. It's going to be bonding to this one sp2 electron at the end here. So I'm going to put a hydrogen here like this. And so I'll just write 1s. And so just remember that this is a hydrogen atom here. And so what you can sort of see here is that this hydrogen atom can form a valence bond with this carbon. And this valence bond is going to be called a 1s2sp2 valence bond, or an s-sp2 valence bond. Now we can do another hydrogen here because we need 2 hydrogen atoms per carbon. So here's a second hydrogen atom. And so here it can bond here with this orbital here, one of these sp2 orbitals. And so let's do the 2 other hydrogens on the other carbon. So I'm going to put a hydrogen here like this, and another hydrogen like that. And then these hydrogens will bind with the sp2 orbital of the other carbon like this. And so now we have created 4 valence bonds. We have bonded 2 hydrogens to one carbon, 2 hydrogens to another carbon, but all bonds are the same. They are all 1s, 2sp2 valence bonds, or you can call them s-sp2 valence bonds. Now, one thing we sort of neglected to do in this process is we have bonded the carbons and the hydrogens together, but we need to do is we need to form a bond between the 2 carbons. And I can see one place where we can do that. And so we can sort of see is that we can form a valence bond here from this carbon hybridized orbital with this carbon hybridized orbital. We can do that is because each of these orbitals only has 1 electron. As you might remember, you can form valence bonds when you have orbitals overlapping that have just 1 electron. So here we can bond these together like this. So this bond here is a bond that connects one carbon to the other carbon atom and has 2 electrons. But we have a problem here in that you can see that in the Lewis structure we need to create 2 bonds between the 2 carbon atoms. So we have to figure out where we can form another bond. Well, one place you might consider looking at is at these core electrons here in the first energy level. Could we form a bond between these orbitals and with the core electrons? The answer is no. It's because these orbitals are already filled, and so no bond will form here. So the question is, what do we do next? Okay, so to understand what we do next, what I'm going to do is I'm going to try to draw a picture of what I have done so far. So what I've done so far is I have bonded 4 hydrogens to carbons, as you can see, and I've also bonded a carbon to the carbon. And just to point out, this carbon-carbon bond is also a valence bond. And here it's going to be a 2sp2 valence bond, or an sp2 valence bond. All of these bonds here are sigma bonds. So all these bonds will have electron densities between the atoms, and that electron density will be symmetrically arranged around an axis that connects the atoms. So what I want to do is now try to draw a picture of these 5 sigma bonds. Important fact about this molecule is all the atoms in the molecule, the 2 carbons and the 4 hydrogens, are in the same plane. So what I'm going to do is I'm going to try to draw a plane here like this. So here is a plane, and my goal is to sort of make sure that all the atoms I've drawn here are within this plane. They're all going to be in the same plane. So we have a carbon here. This is the first carbon. And so here is the valence bond that connects carbon to the second carbon. And so again, this is going to be the sp2 valence bond. And so now I can sort of in the same plane draw in hydrogens like this. This is going to be an sp2 s bond to this hydrogen and to this hydrogen, and then I'll draw these other hydrogens here. Okay, so far so good. So all these are sigma bonds, and so what you can see is what I've done is I've represented with lines the 5 sigma bonds that I have here into the electron configuration. Okay, so now we have to put in a second bond that connects the carbons. Where is this bond? I'll show you where it is. So remember with these electron configurations, we did not hybridize here a p orbital. With each of these carbon atoms, there is an intact p orbital with 1 electron. And what will happen is these p orbitals will form a valence bond. You can call it a pp valence bond, but the way most people call it is they call it a pi bond. So let's talk about where these p orbitals are in this molecule and where the pi bond forms. So you can see again, there are 5 sigma bonds here that are in the plane that all these atoms are in. Now let's imagine where the p orbitals are. The p orbitals are propeller shaped and their lobes stick out from the plane. So they are perpendicular to the plane. So you have one p lobe that sticks out like this from one carbon atom. You have another p lobe that sticks out like that on the opposite side of the carbon atom. And so this carbon has the same thing. It also has a p orbital. And so this lobe sticks out here, and then this lobe sticks out there. So here you can see that the p lobes are either above or below the plane of the molecule. Now what you'll notice is that the p lobes are overlapping. And so this area of overlap is where you have the valence bond form. So this region here and this region here is where the valence bond form. And that region is called a pi bond. Now, an important thing to notice is that here you can sort of see in this orbital notation that the pi bond is comprised of 2 different p orbitals on 2 different atoms, and each of these p orbitals has a single electron for a total of 2 electrons in the pi bond. Same deal. This is not 2 pi bonds I've drawn. I have drawn 1 pi bond with some density above the plane of the molecule and some density below. So it may be better if I erase one of these pi's here, just to indicate that we really have 1 pi bond here. But within the pi bond, you have 2 electrons. And so you can maybe find at one moment of time that these 2 electrons are in the lobes that are above the molecule. Maybe at another time, both electrons will be below the plane of the molecule in those lobes, and then they can be one above and one above. Oh, let me say it again, one above and one below. They can kind of swap places. Okay, so we have that, and so I want to kind of go to the computer here and show you some real pictures of what this looks like, because my drawing is probably not the best. So here I'm just kind of pointing out how you get individual carbon atoms with their atomic orbitals form sp2 hybrid orbitals. And I'm hoping what you sort of see here in this picture is that when you do that, you have a p orbital that is not hybridized, and that could lead to a pi bond. So here's a better picture of what I try to draw. And this is just to point out the orientation of the p orbital in space compared to the sp2 hybrid orbitals. And what I'm hoping you can see here is that the p orbital is sticking out perpendicular to the plane that the sp2 orbitals are at. So just that's good to know. And then so here I have a sort of another picture of the ethene molecule, or ethylene, you can call it either way. And so you look at the top middle picture there, that's sort of a bird's eye view of the sigma bonding network of the molecule. And so there, if you look carefully, is you can see that there are 5 sigma bonds. And so one sigma bond is here that connects the sp2 orbital of one carbon with the sp2 of another. And then you have 4 others which connect sp2 with hydrogen here, and then sp2 with this hydrogen here, and same thing here. So there are 5 sigma bonds total. Now, what you can sort of look at in the lower left picture, now we're looking at the molecule from the side, and you can sort of see where the p orbitals are located. They're going up and down from the carbon atoms. They're perpendicular to the plane of where all those atoms are. And so the final right picture there that you see, you can sort of see there encircled in red is the sigma bonding network, where the sigma bonds are. There are 5 of them. And then what we have are the pi bond that exists. And so it's a single pi bond, but there are 2 areas to it. One area is above the sigma network plane, and one of it's below the sigma network plane. And so here's just another picture of that. I encourage you to look at that. Nothing really unusual here. This just points out that when you have these 2 electrons in the p orbitals, they are found in the pi bonds. And so here in these pictures, I'm just showing 1 electron in one pi bond and 1 electron in another pi bond. This is kind of important. You have to remind yourself this important fact. When you're looking at a double bond in a molecule, you need to remind yourself that one of the bonds is a sigma bond. The other bond really is a pi bond. And so they're kind of different in nature. So if you can remember that fact, that would be very important. And so there's another sort of electron density map of what the molecule looks like. The areas in red are where you find a lot of electrons. The area in blue is where you don't find as much electrons. And so moving on, so here's another picture of it. And so this is just another diagram of what the molecule looks like. You can see the sigma bonding network there, bonding the purple carbon hybridized orbitals with the blue hydrogen orbitals. And then what you see is that you have the pi bond formed. And the pi bond has formed when you have overlap of the p orbital of one carbon atom with the p orbital of another carbon atom. Okay, so I want to go over one more example of another molecule that can form pi bonds. And so this molecule is acetylene. So what I'm going to do is I'm going to quickly draw a Lewis structure for that. And so if you take this molecule C2H2, you will make a Lewis structure, and what you'll find is that here, when you're dealing with the valence electrons, you're pretty much going to have a bond between this carbon and this hydrogen, a bond between this carbon and hydrogen, and then what you're going to have to do to make sure that the carbons have octets, you're going to have to move electrons into the bonds between carbon and carbon. So what you'll find is there actually is a triple bond between carbon and carbon. So this is the acetylene molecule. So now what I want to do is, again, try to understand where the pi bonds form in this molecule by looking at the orbital rotations of the carbon atoms and drawing a picture of it. So here we have a carbon here, and so its orbital rotation is 1s. Okay, now we have to figure out what the hybridized orbitals of this carbon are. Here's the thing. They are not regular p orbitals. They are not sp3 orbitals. They are not sp2 orbitals. There's something else. So let's figure out what they are. So you can see here this carbon has 2 electron groups. The single bond is an electron group. The triple bond is an electron group. There are 2 electron groups. And so from that, you can form 2 hybrid orbitals. The way you form 2 hybrid orbitals is you grab an s and a p. So you're going to create 2 sp orbitals. So here are the hybrid orbitals here. These are called sp orbitals, and there's second energy level, so I'm going to put a 2 there. Now, when we form those hybrid orbitals, we grab 1 p out of 3 p orbitals. And so here, you're going to have 2 unhybridized p orbitals like that. So you can put in electrons and it'll look like this. So this is the electron configuration of a carbon bound to other atoms. And so here the other carbon is the same. So we'll draw this out. And then we have the p orbitals here with electrons like this. Okay, so now what I'm going to do is I'm going to bond the two hydrogens in the molecule. So one hydrogen is bound to one carbon atom, so I'm going to put a hydrogen here, which is 1s. And so it will form a valence bond here with one of these sp orbitals. And so the other hydrogen is bound to the other carbon, so I have to have that here, 1s. And so it will form a valence bond with this sp orbital on the other carbon. And then we have to link the two carbon atoms together with a valence bond. And so we do that here, and this valence bond is going to be a 2sp, 2sp. Let me add a 2 here. Or you can think of it just as an sp-sp valence bond. Okay, so far so good. Now let's go ahead and draw a picture of this and see what it looks like. And so again, all the atoms here are on the same plane, kind of as with the other molecule we were dealing with, which was ethene. And so we have carbon here, bound to carbon here, single bond here, which is going to be this valence bond. And then there's another valence bond to this hydrogen, which is this one. This other carbon has another hydrogen here bound to it, which is this valence bond here. Okay, now this is where the fun begins. We have to figure out where the p orbitals are in reference to these three sigma bonds. So again, I should have made you aware here that these are sigma bonds. So let's think about where these p orbitals are going to be. So this is where it gets kind of interesting. So you will note that each carbon atom has two free p orbitals. So let me draw those right now. I'm going to focus on the left carbon. So one p orbital goes out like this, up and down below the plane of the molecule. But then there's another one, which I'm going to draw on a green pen. And this one is going to be perpendicular at 90 degrees to this p orbital that I just drew. So I'm going to have some of the p orbital head out toward me, and then some of the p orbital head out into the board. Okay, I realize that's not the best drawing, but that's something we're going to have to deal with right now. Okay, so the other carbon here, it too has two p orbitals. And so it will also have a p orbital that overlaps with the first p orbital that is going up and down from the plane. And so here, the second carbon atom also has another p orbital in green, which is perpendicular to the p orbital that I drew. Okay, so how many pi bonds can form? Well, let's count them. One pi bond can form when these two p orbitals on these two different carbons overlap. That's the purple one here, or the pink one, whatever color that is. And then we have another pi bond can form in green when these two p orbitals overlap. And these two p orbitals are on 90 degrees to the first p orbitals there. And so here now you can see that when you have the acetylene molecule, one of the bonds between the carbon atoms is going to be a sigma bond, but another is going to be a pi bond, and the other will be a pi bond. So when you have a triple bond, you have one being a sigma bond, and the other two bonds are pi bonds. And so, like before, what is the pi bond? The pi bond, one pi bond, is just going to be just the overlap that includes here this top overlap for these p orbitals and this bottom overlap for these p orbitals. That's one pi bond with this pair of electrons. And then we have another pi bond that will form between the green p orbitals heading out toward me or going into the board, and where they overlap either out toward me or where they overlap into the board will also carry two electrons. Okay, so let us move on. Okay, so what I want to do is I want to look at the computer, sort of point some things out that I kind of went over on the light board here. And so this is just to point out is how you get the sp hybridization of the carbon atoms in acetylene. So you might remember that carbon, to start with, for its valence orbitals, it has a 2s orbital and 3 2p orbitals, and these can be hybridized. And so here we only need 2 electron groups per carbon. So we only need to grab an s and a p, and they hybridize, forming sp orbitals. And then there are 2 p orbitals that are unhybridized, which I've circled there. And so here are some pictures of the acetylene molecule, and I'm trying to show you here that there on the top left, I'm showing the sigma bond network. And so here we have sp orbitals, which I've written in yellow letters on the brown sp orbital lobes, and they're bound to each other, or they're bound to 1s hydrogen orbitals. That top central picture is showing the p orbitals, which I tried to draw that are perpendicular to one another. I encourage you to look at that. And then the picture on the right shows you how those overlaps of the p orbitals look like as pi bonds. And so that's what the molecule looks like. And importantly, on the bottom left, what I want you to notice is that we have a picture of acetylene, which is C2H2, and I'm hoping that you can see is that those carbons will have 3 bonds. One must be a sigma bond, and then the other 2 must be pi bonds. Okay, and so here's another picture of the acetylene molecule. That's just another way of looking at it, and so that may be a more clear picture so that you can really see that although there seems to be 4 areas of pi density, you have to remember here there are really only 2 pi bonds. And then the density up above and below the plane is 1 pi bond, and then the density heading out toward me and then going into the board is another pi bond. Okay, so moving on from here. Okay, so one of the things you're going to have to do is you're going to have to look at a complicated Lewis structure and figure out how many sigma and pi bonds are found in the structure. So this is actually not so difficult to do. So here what I have is I have a picture of a molecule called acetic acid. And so you will be asked how many sigma bonds are in this structure and how many pi bonds are in this structure. So the sigma bonds are counted in the following way. Each single bond is a sigma bond. If you have a double bond, one of the double bonds is a sigma bond. If you have a triple bond, one of the bonds is a sigma bond. So what you can see is that you have 6 single bonds, and those will be sigma bonds. But then you have one other sigma bond in the double bond there. So you have a total of 7 sigma bonds. Now, how many pi bonds are there? The only place you can look for a pi bond is in a double bond. When you have a double bond, one is going to be sigma and one's going to be pi. And so you can see there that other bond going to that oxygen atom from carbon is considered a pi bond. So this molecule has 7 sigma bonds and 1 pi bond. Okay, how about this structure here? So this is kind of a related question. How many pi bonded electrons are found in this molecule, which is called aspartic acid? So what you have to do is sort of, first off, know which bonds are pi bonds, and then second off, you need to know how many electrons are found in a pi bond. So you cannot find a pi bond in any place where you see single bonds. The only place that you can find a pi bond is it's going to be one of the bonds in the double bond. So here is a pi bond here, which I'm circling here between the carbon and the oxygen. And so that will have 2 electrons. And then here's another pi bond here between this carbon and the oxygen. And so that has 2 electrons. And so there are a total of 4 pi electrons in this molecule. Last question. In these pictures, can you count the total number of sigma and pi bonds? Let's go through this. So picture number 1, which is hydrogen cyanide or cyanide gas. Ugh. Okay, how many sigma and pi bonds are there? So what I'm kind of hoping you can see is that this carbon-hydrogen bond is a sigma bond, and then one of the bonds in the triple bond from carbon and nitrogen is a sigma bond. So we have 2 sigma bonds here in this molecule. How many pi bonds do we have? Well, the triple bond, the other 2 bonds are pi, so we have 2 pi bonds in this molecule. Okay, the next molecule is a little bit more complicated. So the sigma bonds are 1, 2, 3, 4, 5 sigma bonds, and then one of the bonds in the double and one of the bonds in the triple is a sigma bond. So it looks like we have 7 sigma bonds in this molecule. Now, how many pi bonds do we have total between these atoms? So it looks like there's 2 pi bonds connecting the other 2 carbon atoms in the triple bond. So it looks like we have 3 pi bonds here. And so the last molecule, I'm going to pause the video so that you can sort of figure out how many sigma pi bonds are there. And now I will tell you the answer. It looks like there are 13 sigma bonds, and there are 0 pi bonds here because I don't see any double or triple bonds. Thank you for listening. We will see you next time.